Okay, good. Uh, okay, we'll start a new topic from now on. Okay, we'll deal mostly with complex numbers now, and you'll learn how to think of complex functions. Just like real functions, you input a real number. I vaguely put. You input a real number, you get output a real number. For example, f of x equal to x square, right? You input 2, you get 4, right? So similarly, you will see now that I can think of complex functions as well, where I input a complex number and I get out a complex numbers. And again, so before doing complex functions, we will first do complex numbers. Okay, fine. Again, so we'll revise what you have already learned in your class 12th probably. So some of the aspects of complex numbers, and then we'll slowly transition into complex functions. Okay. Okay, so what are complex numbers? Simply put, it's a set of numbers, okay, which is basically a combination of two real numbers. Okay, typically the formal way of writing is C is a set of numbers of the form x plus iota y, where x is a real number and y is also a real number. So this should be real and this should be real. Okay? So then an iota is the imaginary unit. And it has some properties that we define. Okay? These properties are iota square is minus 1. Okay. Basically, I don't know what iota is, but I know what happens when iota multiplies iota. Okay. It squares like a usual number, but it squares to minus 1. Okay. So and another way of writing iota is square root of minus 1, which we don't know how to quantify this object. So we keep this object as it is. Okay. Iota square is minus 1, iota cube is minus iota, and iota to the power 4 is back to 1. Okay? The other two follow from this, right? Because if you multiply with iota, you get iota cube is minus iota, right? And you multiply with iota, again you get iota to the power 4 is minus iota square, but iota square is minus 1, so it becomes plus 1. Okay? Now, you will see that this set of numbers, just with this little tweak, that iota square is minus 1, you will see it leads to amazing consequences. And while it may not appear from this, but it has tremendous applications in physics and mathematics as well. Okay, you might have already known some applications, but we will learn slowly. Okay, what applications does it have? Okay, but this simple additional construct on this set that iota square is minus 1 leads to some very good results. Okay, very useful ones. But that for later, this is the first defining characteristic of the set, that iota square is minus 1. Okay. Now, when you define numbers, the next thing you should know how to add them, right? I mean, that's the natural progression. Right? How to add them, how to multiply them, basically how to do algebra with them. Okay? So algebra, all the algebra is the usual algebra, right? Whatever you do with real numbers, but you have to take into account this additional construct that iota square is minus 1. For example, if you want to add two complex numbers, z1 and z2, okay? So let's say z3 is z1 plus z2, okay? And z1, so there would be two real numbers associated with z1 and two real numbers associated with z2 as well. Okay? So let me call them as x1 plus iota y1. So these are the two real numbers associated with z1, and x2 plus iota y2. These are the two real numbers associated with z2. So we find that x1 plus x2 plus iota y1 plus y2. So this is how you add the two complex numbers. Okay? Huh? Fine. Similarly, if I multiply the two complex numbers, okay, here we didn't use this fact that iota square is minus 1 because we didn't need to. We know about iota square. But let's multiply two numbers. You'll see that we'll get iota square out of it. Okay? So if I multiply z1 with z2, I'll get x1 plus iota y1 times x2 plus iota y2. What do I get here? x1, x2, right? First, I would like to calculate things without iota. Okay? First one is x1, x2, right? This is the first thing, right? The other one is when iota multiplies with iota, because you see that when iota multiplies with iota, you get iota square, right? Which is not a complex number, but well, it's a complex number, but it's equal to a minus 1. It's a real number also. Okay? So minus y1, y2, right? So these are the numbers without iota. Plus, when I do with iota numbers, I get x1, y2 plus y1, x2. Right? So these are the usual things that you learn. Okay? So this is the multiplication of these two numbers. Okay? Now you would have noticed one thing, that if I add two complex numbers, I get a complex number, right? Fine. Now if I do some linear combination of these complex numbers, I'll still get a complex number, right? If I multiply like 3z1 plus 4z2 or some alpha z1 plus beta z2, it's still in the same set. So what do you call such sets? Vector spaces, exactly. So this set of complex numbers forms a vector space under this addition, okay? So a vector space of what dimension? How do you figure out a dimension? Right? Its dimension is 2. Why? Because you need two real numbers to specify one number, right? One complex number. Okay? So sometimes this is called maybe later. Okay. So let's go ahead. Okay. Now we will learn about two other things, another way of representing these complex numbers. Okay. See, you can immediately see there is a close resemblance of the way we write complex numbers. Basically, I need two real numbers, and I specify a complex number, right? No. So you have already done this with vectors, right? If you give me two real numbers, and if I interpret them as some components of a vector, okay, I can represent them on a plane, right? So I draw a Cartesian plane, then any point on this plane, so there is a length along this and the length along this, okay? These two lengths together give you this vector, okay, which represents this point, okay? And you call this to be the position vector of this point, and it is basically an ordered pair x, y, right? Where these two have physical identification, that this is the distance from the y-axis and this is the distance from the x-axis, perpendicular distance, okay? So this is quite a similar story with complex numbers, okay? But remember, now there is an additional construct. What? Iota square is minus 1, right? So instead of thinking this as this point to be represented by a position vector, we'll think of this point to be represented by a complex number with same real part, with the same coordinates, if you wish, x plus iota. Okay? Where x is the length from here to here, y is the length from here to here. Okay? So now you can interpret this point itself as an identity that it represents a complex number. Okay? This is sort of, not even sort of, this is exactly similar to the idea of this number line, right? That you learn in class 10, right? That every point on this number line, right, represents a real number. Okay? Now, see, note that as we move from minus infinity to infinity on this number line, there is a direction in which you are moving, right? From smaller numbers to bigger numbers, right? So you can think of these real numbers to be ordered, right? One is bigger than other, okay? But you see, there is no way of figuring out whether one is bigger than other between two complex numbers. Let's say if I take a number here and a number there, okay, there's no way to order them, okay? So the complex numbers are not ordered basically. So things like this, that z1 is bigger than z2, this does not make sense. Okay? This is the stupid thing to write per se in this. Okay? Okay. So now let's in your Cartesian plane there were two ways of representing this number, right? One, when you give me this distance and you give me this distance, I can represent it with a position vector, right? But this position vector you can write it in other ways, right? This is the same information can be carried out in other ways, right? For example, I can give you this angle, but that is not enough. You need to tell me how far I need to move from this point to reach that point, to reach basically this point A, whatever. Okay. Now, so there are two other things, right? The r and theta. Okay. So let's figure out what they are in terms of this language, this new language, right? Okay. So r, you know, is basically square root x square plus y square. Okay. What? It's the length, basically Pythagoras, right? But this is wait. Okay. This is also basically the square root of the first number square and the second number square, right? And theta is what? Tan inverse x by 1. Sorry, y by x. Okay? Huh? Right? Now this is called mod z. It is the modulus of the complex number. Okay? It's the usual way of representing this in terms of the complex number. This is called mod z, and this is called argument of z. Theta is called argument of z. Okay? So the polar coordinates r and theta, okay, transformed into the complex language are basically the modulus of this complex number and the argument of this complex number. Okay? Right? Now, notice that if I multiply two numbers, z, x, let's say I have a complex number x plus iota y, and I multiply it with x minus iota y, okay? So these are two perfectly good complex numbers, right? If I multiply the two using usual multiplication rules, what do I get? I get x square plus y square. If you do the algebra, which is pretty straightforward, okay, you will get x square plus y square. Okay? Huh? Yes. Okay. So if this complex number is z, we associate another identity to this complex number. Okay? Because this is essentially the same complex number, except what you have replaced iota with minus iota. So we call it complex conjugate of. We call it complex conjugate of this complex number. Okay? So if this is z, the way to represent complex conjugate, there are ways to represent. So one way to represent is put the z and put a bar. So this is a number which is complex conjugate of this number, of this number z, whatever you are calling z. So z bar, so this gives an equation which might be useful, right? Quite often simple equation. Z bar is basically, this is mod z square. This x square plus y square is just mod z square. Good. Okay. So now think of this z bar, which is keep the real part same and replace iota with minus iota. Okay. Okay, I didn't tell you what real part is, but I'll come to it. It's a very simple thing. So you just replace iota with minus iota. So if I represent this on my plane, okay. By earlier this was just Cartesian plane. Okay. Now we will call it complex plane. Okay. The reason to distinguish is just the fact that every point now represents a complex number. So if z is here, okay, there is this number x and there is this number y. I'm pretty bad at drawing, but I hope you can excuse that. So there is this number x, real number, and there is this real number y. Remember, since they were real numbers, we could to associate them with some distances. Okay? So where does z bar sit? Z bar has same x, so this is z basically, this point. Okay? Now z bar sits where it has same x but equal and negative y. Right? Okay? So then this is basically z bar. Right? Perfectly symmetric. Okay? So modulus of the two would be same, obviously, right? Because symmetry, right? What about argument? What about argument? If this guy has an argument of theta, z. What about argument of z bar? Minus theta. It's simple. So argument of z bar is just minus argument of z. Okay? And it is in some sense, not in some sense, it is exactly the mirror image of this guy. Imagine a mirror here, it just reflects. Okay? This is clear? Okay. Any questions so far? This is just basic, okay? Let's move ahead. Now, these two numbers which represent z, okay, there is a distinction between the two. One of them comes with the iota, the imaginary unit. The other is without the imaginary unit. Remember, z is equal to x plus iy. These two are real numbers. Okay? So, this guy is called the real part. Okay? And this guy is called the imaginary part. Okay? Pretty straightforward. Nothing here, just labeling things. Okay? Now, if I want x in terms of z itself, you can see that I can write x as z plus, you add its complex conjugate and divide it by 2. So the real part is basically x is equal to z plus z bar by 2, and the imaginary part is just z minus z bar divided by 2y. Remember, this iota comes because z minus z bar will give you 2 iota times y. When you divide by 2 iota, you will get y. Okay? Okay? Let's move ahead. Now you can represent the complex number two ways, right? So one is z equal to x plus iota y. Another is you tell me what is the modulus of the complex number and what is its argument, basically. What is theta and what is r. Okay? Since these two things represent the same information, there should be a way to go from one to another. Right? So if I want to write x in terms of r and theta, what do I write? R cos theta, right? And y in terms of r and theta is r sin theta. Same principles work because these are distances, right? So same principles what you learned in 2D vectors work, okay? But with this additional construct, right? Because iota square is minus iota. Okay? There was nothing like iota square. You had I hat, j hat, and then you had dot products and cross products. Okay? So if I put x as r cos theta, y as r sin theta, I get r cos theta plus I sin theta. Okay? I just took r as common. Okay? R is basically mod z. It's the modulus of the complex number. I get cos theta plus. Is it fine? Now, this object, this cos theta plus I sin theta, okay? You can represent it as an exponential of something. Okay? So we know that this is mod z. This is nothing but e power I theta. Okay? How do I show cos theta plus I sin theta is e power I theta? Do you guys know? Huh? Huh?
Euler's identity.
No, Euler's identity is this e power I pi plus 1 equal to 0, I think. This is Euler's identity. You want to show that, you want to show this thing, cos theta plus I sin theta is e power I theta. This guy you want to show. This is, I think it's called de Moivre's theorem. Or de Moivre's formula or something. This is called de Moivre's formula. You don't know? Okay? Huh? What? Okay, it's fine. So, one way of doing it is to write a Taylor series for cos theta. Okay? So, if I write a Taylor series for cos theta, if I write a Taylor series for sin theta, if I add them, okay, I'll get a Taylor series for e power I theta. Do you remember the Taylor series? Right? So, what is cos theta by Taylor series? Sure? It is 1 minus theta square by 2 factorial plus theta cube by 3 factorial plus so on. Okay? What else? Sin theta is what? Theta.
Theta plus.
Oh no, wait, sorry. Cos has even powers. Yeah, theta to the power 4 by 4 factorial. Remember, these are just obtained by taking derivatives, right? And sin is theta minus theta cube by 3 factorial. Is this minus?
Plus.
Plus. Okay. Yeah. Is this minus or plus? Plus theta to the power 5 by 5 factorial. Plus so on. Yeah, I think there might be a minus sign here. Okay. So now, what is cos theta plus I sin theta? Okay, let's just do. I'm a bit worried about this. So obviously, what are we doing Taylor series about? Right? Taylor series, you have to select a point. Right? We're doing theta around theta equal to 0. Right? So for any function f of theta, okay, how do I do the Taylor series? First f of 0, then f prime evaluated at 0 times theta plus f double prime evaluated at 0 theta square by 2 factorial plus so on. Right? So what is sin theta evaluated at 0? It is just 0. Yes. Good. So what is the derivative of sin theta? It is cos theta. Right? Yeah. It's cos theta or minus cos theta? Cos theta, yeah. So it is cos theta, so cos theta evaluated at 0 is just 1, so I get theta. Is this clear?
Yes, sir.
Now this is double prime, so sin theta will remain sin theta, right? And if you put 0, yeah, minus sign won't matter because you put in 0, so it will be 0, minus 0. Okay, then when you differentiate again, I'll get minus cos theta, right? Which evaluated at 0 gives me what?
1.
Okay? Is this fine? Huh? But there is a minus sign. So there is a minus. Okay, alternate minus signs. Minus theta cube by 3 factorial. Okay. Plus theta to the power 4 by 4 factorial. Right? 5.
Even odd power.
Yeah, odd power. Theta to the power thanks. 5 factorial. Okay. Then minus whatever theta to the power 7 plus. Okay, what is then cos theta plus I sin theta? It is 1. Okay, I'll write the increasing powers of theta. This contains even powers, this contains odd powers. So when I add, what do I get? 1 plus I theta, right? Power 1. Power 2 will come from here, minus theta square by theta square by 2 factorial minus I theta cube by 3 factorial plus theta to the power 4 by 4 factorial. I is coming only with sign because I had multiplied this plus so on. Okay? Yes. But okay, I want to show that this is the same as e power I theta, right? Yes. So let's do e power I theta Taylor series of this. So what is the first term? No, what is the first term when you do Taylor series? 1. This is 1. Okay, what is the second term? Iota theta. Yeah, so theta is this, yes, right? If I have to evaluate it 0, so 0, it will become 1, but iota will come down due to differentiation, right?
Yes, sir.
Iota theta. Okay, then what else? Plus iota square, theta square, right? Divided by 2 factorial. Then iota cube, when you differentiate it thrice, you bring down iota 3 times, but then put theta equal to 0, e power iota theta will become 1.
Yes.
So iota cube will remain, right? So iota cube, theta cube, divided by 3 factorial, right?
Iota power 4.
Then, yeah, I power 4,
Theta power.
theta power 4 divided by 4 factorial. Okay? This is the first time you will see this iota square equal to -1, giving you something which is different from usual. Okay? Iota square is what?
Minus.
Iota cube is minus iota. See, this is matching because of this. 1 iota theta, right? Iota square is -1, so it will become minus theta square by 2 factorial is the same as there.
Yes, sir.
Okay? Iota cube, theta cube by 3 factorial, but iota cube is minus iota, it makes the same as this term. And these are now 1 to 1 same, right? Every term is same, every power of theta is same.
Yes, sir.
The same coefficient, right? Iota power 4 is 1 this. But this was possible, why? Because yeah, the Taylor series, yeah, but this was possible, why? Because iota square was -1. Right? This is the first time you see its effect. This simple construct gives you this beautiful equation, cos theta plus I sin theta is what? Is e power I theta. Okay? Huh? Right? Now see, this has another consequence. This stems from what? Iota square is -1. Obviously, we use Taylor series to prove it, but that may not be the only way. There might be others. Okay. Let's say I have cos of n times theta plus iota sine of n times theta. Okay? Right? What did we learn here? Cos of whatever you have in the argument plus iota sine whatever you have in the argument is e power iota whatever that number is in the argument. Okay?
Yes, sir.
But make sure that this theta is real, don't use for imaginary. Okay, this theta is a real number, right? This equation we derived for a real number.
Yes, sir.
So cos of n theta, n is some any number, whatever it is. This should be equal to e power iota n theta, right? है ना?
Yes, sir.
But this should be same as what? It is e power iota theta raised power n. The same thing, right?
Cos theta plus iota sin.
But e power iota theta is cos theta plus iota sin theta. So this gives you another equation that cos of n theta okay.
Yes, sir.
You can use this relation to derive any formula if you wish. If you want to know what is cos 2 theta, okay, you can get it from this. Okay. Huh? There's one more thing to note which I forgot to mention earlier is when do you say two complex numbers are equal? Obviously, I can't say this complex number is bigger than that complex number, this complex, that those things I can't say. But I can certainly say when two complex numbers are same. Okay? The principle is same as for vectors, right? When was 2D vectors, when were they equal? When their components are equal, right? In I hat j basis. Same idea applies here. Okay? So two complex numbers are same, okay, when their real parts as well as imaginary parts are equal. Okay? Every complex equation therefore gives you two real equations. Okay? Because if z1 is equal to z2, that implies the real part of z1, which let's say x1, is the same as real part of z2, which is let's say x2, and imaginary parts are also same. Okay? This equation, this is a complex equation. You are saying the two complex numbers are same. Okay? That is equivalent to saying that these pairs of real numbers are same. Like x1 equal to x2, then y1 is equal to y2. Okay? So these are real equations, no complex business involved here. This is a complex equation. Okay? Every complex equation gives you two real equations. Okay? whenever you talk about equating complex numbers, okay, you basically talk about real parts are same as well as imaginary parts are same. Only then the complex number is same. Okay? So now let's use this idea here. So what you derived was cos of n theta plus iota sine of n theta is cos theta plus iota sine theta raised power n. Okay? Good? Huh?
Yes.
Now you see that while deriving this, we didn't assume anything about n. Okay? So this is an identity basically that it will work for any n. Okay? N should be the only thing n has to be is real. It has to be real. Okay? Because whatever this duration we derived for theta to be real. So whatever the argument has to be real. Now let me put n equal to 2. Okay? What do I get? I get cos 2 theta plus I sine 2 theta, right? Huh? Is the same as cos theta plus iota sine theta ka square, right? So I can just square this guy. So which is a square plus what is that? Cos square theta, right? Plus what? Iota sine theta square plus 2 iota cos theta sine theta. Right? So what do I get from here? I get that this should be cos square theta minus sine square theta plus iota times 2 cos theta. So what is the real part of this complex number? This part, this guy, right? And what is the imaginary part of this complex number? This guy, right? Remember, you can only call them real and imaginary parts if they are itself real. Huh? Okay? Huh?
Yes,
So let's equate the real parts. What do we get? Cos 2 theta is cos square theta minus sin square theta, and I get sin 2 theta is equal to 2 cos theta sin theta. Okay, these are the so-called half-angle formulas, if you remember, right?
yes.
So you can just use this equation to get, let's say, cos 3 theta or cos 4 theta, whatever, in terms of just right? Just squares and cubes of what? Cos theta, right? Cos theta and sin theta, right? Okay? Huh? But you should remember these two because you will use them very frequently. You don't want to derive them again and again. Okay?
Yes, sir.
Okay. So this was a short, say, detour into this interesting thing that came out of it. But let's go back. So what we showed was z equal to x plus iy is the same as mod z cos theta plus I sin theta, which is the same as mod z equal to that. Okay? And this is called polar form. Polar form of the complex number. Polar form comes from the word polar coordinates, right? Because using polar coordinates. And this is called, I think, Cartesian form. Okay. So obviously you can go from this to that. Okay? Okay. So let me take this argument again, right? So I have this complex plane and I have a complex number z here. Okay? So it has an argument theta, which is what? Tan inverse y by x. The imaginary part by the real part. Okay? But somebody might come and say that I don't want to use theta, I want to rotate by 2 pi and then add theta, which is also a perfectly valid argument. Okay? Eventually you have to reach this point. Somebody might go around, okay, and then come here. Right? So what is his argument then? 2 pi plus theta. Okay? But somebody might go around twice. plus theta. But eventually, as long as the modulus is same, you are representing the same complex number, right?
Yes, sir.
Right? There is no difference. So this polar form is not unique. There are multiple ways of representing it. Okay? So I can write z as mod z e power I theta, right? Which is the same as mod z e power I theta plus 2 pi, right? Which is the same as mod z e power I theta plus 4 pi. Okay? Theta plus so on, right? Theta plus 2n pi, not n pi, 2n pi, right? You have to go fully over. N pi will go fully over. For n equal 3, you are not going. You will end up here. Okay? But that would mean, this would mean if these two are indeed same, then e to the power 2i n pi should be 1, right? Huh? This number should be 1. Then it would imply that you are just multiplying 1. You are doing nothing to the complex number. Okay? That's indeed true, because we learned from De Morgan's theorem, we learned that this is cos 2 pi plus iota sine 2 pi whole to the power n. But what is cos 2 pi plus iota sine 2 pi?
Cos pi plus sine iota sine pi to the power 2.
What is cos 2 pi?
Cos theta.
Huh? What? Yeah, what is cos 2 pi?
It's cos 2 pi.
Yeah, 1. It's just 1. And sine 2 pi is just 0. So it's just 1. Okay? Yeah, one thing that is a bit confusing to me, but I'll come back later. Maybe I said something wrong, which I will correct later. Yeah, maybe I'll correct. Okay, so this is just 1. So e power 2 iota n pi is just 1. So e power, if I think of a function e power iota x, right? This is periodic. With period what? 2 pi. Then and you take x. Okay? That's why in complex Fourier series, if you remember, we use this thing as our basis, right? These functions, chi n of x e power iota 2 pi n by L times x. Something like this. So its period was what? L. No, its period was L, right? We had rescaled x so that the period is L. Okay? Right? The period is when this guy becomes 2 pi, 2n pi or whatever. So when x is L, right, the period it becomes 2n pi, which is the period. Okay? The n times period. Okay. Is this okay?
Yes.
Okay, nice. So we basically learned a few things, okay? That how to represent the complex numbers, how to add them, and how to manipulate them here and there, right?
Yes.
Now, remember, these representations, they might look same, but they are still useful, okay? They're useful in the sense that if I have, let's say, I want to take z to the power 1 by 2, okay? I have a complex number, I want to take it square, basically. So let's say my z is mod z. My z is mod z e power I theta. Okay? And theta lies between 0 and 2 pi. Okay? I'm working with this representation, this one. Mod z e power I theta. Okay? So for that, you can't go around. You just once. Okay? I want to calculate some other complex number w, okay, which is z raised to power 1 by 2. So I want to raise this, take the square root of this complex number, okay. So I will get obviously mod z to the power 1 by 2 e power I theta by 2. Okay? No?
Yes.
is just putting 1 by 2 here and then just doing usual algebra. Because I told you usual algebra works with an additional construct. What? Add to square is minus 1. Okay. This thing. Which is basically what complex number? Okay, it's so if my z was this, right? Where is w? Okay. First, w has a modulus of square root z, right? So then it would be let's say mod z is bigger than 1. Otherwise, I think if mod z is so it has some modulus square root z, right? Okay, but it has an argument which is what, half of this argument, right? So if this is theta, when theta by 2 and it is somewhere, let's say here, this is w, this is basically square root z. Okay, this is this complex number. Okay, when you square these complex numbers, okay, you will get what? Good. Now, what if somebody takes this representation? Right? Okay, let's see what he gets. Okay, that guy is doing the same operation. Okay, he's doing the same operation, but he gets plus 5. Right? He is using this representation. This guy. The other guy. Huh? So what does he get? E power I theta by 2 plus 5. Where is this complex number? Obviously the modulus is same, but the argument is different. Right? He gets theta by 2 plus 1. You take theta by 2, right? Plus and then add pi. So he gets which is here. Alright? So he gets a different complex number. Right? So these representations are not quite useless. They're useful. Because if you are taking square root or cube root, same thing will apply when you take cube root. Okay? You will get new complex numbers. Okay? But does that mean I'll get infinitely new complex numbers? Huh? Where should it stop? Huh? Where should it see, does that mean the guy taking the third one will get a new complex number? Let's see what he gets, okay? So this was the first guy used. The second guy, okay? The third person takes z3, the third representation, right? He once again gets mod z to the power 1 by 2, same complex number, but his argument is now e to the I theta by 2. What do I have here? 4 pi.
Plus 2.
Theta by 2 plus 2 pi. But you see 2 pi is redundant right here. Right? Equal. So you're doing theta by 2 plus 2 pi, you end up here also. Right? So after 2 representation, you start repeating. Okay? So you will get the same number. So you won't get infinitely many square roots. You will get only 1. 2. You get my point? If you are doing a cube root, z to the power 1 by 3, what do we get? The first representation will give you something else. Second, something else. And third, you'll get first 3 would be different.
And 4 will repeat
Four will repeat the same.
after 3.
Okay? Good? Okay. So the representation, all of these representations might be fine. All of these representations are equivalent. But if you take square root or in general if you want to do any function with this, okay, then these might give different numbers. Okay? Now this is basically what we are doing when we are finding the roots of the complex number. Okay? Basically, let's say if I have a complex number, when I raise it to the power z to the power n, okay? Let's say I get some z naught. This is so z would be the nth root of z naught. Okay? So how many solutions do you expect? not for now let's just use r not equal to 1. Okay? So how many solutions do you expect for this equation?
N number of solution.
How many? N. Right? Huh? But you see that when we are doing real numbers, x to the power n equal to 1, how many solutions do you get? Only one. There is only one real. X equal to 1. But in principle, this is a polynomial, right? You should have n different solutions. But you learned in your that there are real solutions and there are some of them are there are complex solutions, right? So now we are in a domain where we can actually figure out those complex solutions. Okay? Fine? Huh? I will choose z to the power n equal to 1. You will do z to the power n equal to whatever, z naught. Okay? Assume some number, 3 plus iota, whatever. Okay, good. Huh? Right? So what operation do I need to do? Right? I just need to do an nth root of unity. Right? And you saw here to get different numbers, right? What should I do? I should use different different representations. Right? So first I need to write 1 in what form? In the polar form. Right? So 1 is where in the complex number 1 is where it is here, right?
Yes.
This 1 is here. 1 means real part is 1, imaginary part is 0, which means it's here. So what's its argument? Huh? Argument. Argument is 0. Good. What's its modulus? 1. So it's just 1 is basically e power iota 0. Right? But this is one of the representations. What are the other representations? E power iota 2n pi. Right? These are all the other representations. So z to the power n is basically e power I 2m pi. If I'm using the mth representation. Okay? Huh? So that immediately gives you my z should be what? E power I 2m pi by n. Okay? Huh? And till what should m go? Right? 0 to what? Infinity. But you will start repeating if you remember. Right? So m equal to 0 will give you a new number. M equal to 0 gives you 1. Right?
Yes, sir.
Which is expected, right? Because z to the power n equal to 1, 1 is indeed a solution. Right? Z equal to 1. But what else are there? 1. Right? This is 2 pi by n. M equal to 1. Gives you a new solution. But when will you start repeating?
12.
Huh?
And
There are two ways of figuring it out, okay? One is, remember how many solutions you need to have? N. You can't get more than n, right? Right?
Yes, sir.
So, up to 1 should m go. 0, 1, 2, so on up to n minus 1.
Yes, sir.
Another way of figuring it out is, what happens when you take, let's say n. If you take n plus, if you take, let's say n, what happens? Okay? If I take n, I'll get e power iota 2 pi, which is 1 again. So you're repeating again. Okay? So you're once again repeating. So these solutions are not independent. These solutions are different. The rest are representations of the same solution. You're just adding 2 pi. Okay? These are basically the nth roots of unity. Okay? Is this clear?
Yes, sir.
Is this okay?
Yes.
Now, what have you learned about? Do you know about? Now, let's try to work a bit more with these nth roots of unity. I'll do nth roots of unity. You guys do nth roots of any complex number. Let's say 1 plus iota. Okay. All you need to do is first get it in a polar form. Then use different representations of the polar form to get different numbers. But you need to be careful because you will start repeating after a while. Okay. Huh? Now, let's try to figure out some relations. Okay, let me call this as omega m because this is the mth solution to the nth root of unity. Okay, and m goes from 0 to n minus 1. Now, if you remember quadratic equation, there were relations between what? Zeros, right? This is a polynomial, right? So there was a relation between, for quadratic equation, there was a relation between what? Zeros and the coefficients, right? How did you derive those relations? How did you know that the sum of zeros is basically what? The third term divided by minus c by a, or whatever. And their product is what? B by a. Right? How did you know that? How did you derive it? The way to derive it is to assume two zeros and try to write down a polynomial which has those zeros. Okay? You will automatically get the coefficients as a function of those zeros, sums, whatever. Let's see what we get. Okay? So let's say I have a quadratic polynomial and I am giving you the zeros. How do I write a polynomial p of, let's say, x or z, because we are doing complex numbers, a polynomial of z, okay? Which has, let's say, I don't know, which has two zeros, okay? And let's say they are z1, alpha 1 and alpha 2, okay? Can you write a polynomial which becomes 0 when you put alpha 1 and which becomes 0 when you put alpha 2? Well, how about this? How about this? Put alpha 1, you get 0. You will get 0. Right? Now if I multiply, it will be more of a polynomial that you typically see. What? Z square minus alpha 1 plus alpha 2 times z, right? Plus alpha 1 alpha 2. Okay? So this is the polynomial. So what is the second term? It's minus times sum. What's the third term? Product. Right? These are the coefficients now, right? This guy and this guy. Right? But remember, the coefficient of z square is 1. So let's compare it with the polynomial with coefficient of z square to be 1. Because you can always take that coefficient out and make it 1, right? So what do we get? Z square plus ax plus, z square plus bz plus c. So what is b?
Minus alpha 1
Minus alpha 1 plus alpha 2. What is c? Right? It's because this term is 1. So this is how you figured out that sum of zeros is basically minus b by a. Right? A was 1. A is 1. And product of zeros is just c by a. How do I generalize this? I want to generalize it to let's say a polynomial of degree n. How do I do that? What do you think I should do? So I should repeat the same procedure, but for how many zeros? N zeros. If a polynomial degree n zeros, right? Okay. So can you write a polynomial? Can you get me a polynomial which has n zeros, and these zeros are known to you: alpha 1, alpha 2, so on up to alpha n. Okay. What should it be? Z minus alpha 1, Z minus alpha 2, Z minus alpha 3, so on up to Z minus. Good, perfect. This gives me a polynomial. This is a polynomial, right? Okay?
Yes, sir.
And I know, and this is expressed in terms of its zeros: alpha 1, alpha 2, alpha 3, so on up to alpha n. Okay? I will come back to this guy. Okay? Because this will give us something interesting. Because here we know the zeros, right?
Yes, sir.
First, I think this you should know.
Yes.
Okay, now let's multiply this. What do we get? Okay, now you have to be a bit smart in multiplying. Okay? What is the first term? So obviously from every bracket I can pick. So you will get all possible combinations.
Yes, sir.
Right? This long polynomial that we write, you will have all possible combinations. Okay? Huh? So instead of like multiplying in दोनों को फिर इन दोनों को, think of multiplying like this. I pick up a term from every this and then multiply. Huh? So let's say I want the coefficient of z for n. First you know that the form would be z to the power n. उसके बाद z to the power n minus 1 कुछ coefficient होगा पीछे, उसके बाद z to the power n minus 1. ठीक है ना? पहले z to the power n का देखते हैं. You will get z to the power n only when you pick up what? Z everywhere and multiply. You get z to the power n. So z to the power n is done. Let's just see what about the coefficient of z. Okay? How do you figure out coefficient of z? Okay, tell me one way of choosing from brackets so that you get z.
The first thing is z, bar is z. अब alpha के साथ alpha 1 alpha 2 के साथ multiply करना है z.
Exactly. हाँ? Alpha. So उस term का coefficient क्या होगा? So obviously z आएगा.
Yes sir.
What?
Sum.
Product.
You put up every term and then multiply that with one term here. है ना?
Products of all the zeros.
Except one.
Except one, which one? This one, alpha 1. Good. So let me call that as P1. This is product of all except one.
Yes.
Now what about, is there any other choice? Is this the only possible choice?
No. Product of two.
No, you just want Z.
Yes sir.
So P1 is basically alpha 2, alpha 3. Oh, there is a minus sign, right? Okay. This is minus 1 to the power n minus 1, alpha 2, alpha 3, so on up to alpha n. Do you agree that P1 should be this? Because minus n minus 1 times.
Yes sir.
And alpha 2, alpha 3, because I have commented out alpha 1.
Yes sir.
What about, is there any other choice? Or is this only possible choice?
Total product.
But what choice you need?
Total alpha product divided by
No, that's fine. That's just expressing P1 in a different manner. I'm saying, is this only possible way I'll get Z?
No.
Is there any other way? So what did you do for this? Then you picked up Z from here and then alpha from here. Right? Is there any other way? So when you multiply, you will get Z to the power what? No, wait, sorry. Oh no, we should go there. I'm so sorry. Let's redo this. Sorry, because I did Z to the power n. Then I should do Z to the power n minus 1 Z, not Z. Okay?
Yes, sir.
So obviously Z to the power n only one way, right?
Yes, sir.
Okay? You pick Z from every bracket. What about Z to the power n minus 1? Okay. Tell me one choice which will give me Z to the power n minus 1.
Z power n minus 1 by into
Product of all the respective zeros.
Z, and then
alpha.
one of them you leave. Right? You don't pick Z from, you pick Z from everyone there except A जगह से नहीं लेना.
Yes, sir.
Right? Huh? Let's say I don't pick Z from the first bracket. So what will I get? Minus alpha 1. Z to the power n minus 1.
Yes.
But is this the only possible choice?
No, sir. दूसरे से नहीं ले सकते हैं.
दूसरे से ले सकते हैं, लेकिन वो दूसरी टर्म होगी. Do you get my point? It will add to this term. So, as I told you, that the way to think about this product is you pick one term from every bracket, multiply them, that will be one term. Pick again some different choice, multiply them, that will be another term, plus that term. So, if I pick from the first bracket, I pick alpha 1 minus alpha 1 in terms of, instead of the other one.
N minus 1 times
So, what do I get in general? Minus alpha 1, minus alpha
alpha 2,
minus alpha
3,
minus alpha 4, so on up to. What is this? This is the negative of sum of zeros. Okay? Okay. Good. So this is x by n minus 1. What about n minus 2? What about z for n minus 2? What possible choices do I have?
सारे x से दो से नहीं है.
We'll take from everywhere except two of them. No, depending on which two you choose, you will have a lot of terms in
Yes,
it.
sir. या minus alpha.
ठीक है ना? जैसे और दूसरे से नहीं गया, पहले और
तीसरे से नहीं है।
ठीक है ना, तो कैसा आएगा माइनस अल्फा 1 अल्फा 2, राइट, बिकॉज हर जगह हर दूसरी जगह हमने z लिया है तो वो कॉमन आएगा सबसे, एक्सेप्ट अल्फा 1 अल्फा 2 माइनस अल्फा 1 अल्फा 3 माइनस अल्फा 1 अल्फा 4 minus so on. Okay, sorry, minus minus will become plus now.
Yes, sir.
Right? Plus, plus, plus. Okay? Then plus alpha 2, alpha 3. Plus 1, alpha 2, alpha 4. Every possible combination. Right? Every possible. Take two.
Yes, sir.
Right? Take two of them. Every these zeros, take every possible pair of these zeros. Right?
Yes, sir.
Similarly, when you continue this progression, what do you get? I'll get z to the power n minus 3. Now, 3 of them. So,
Alpha 1, alpha 2, alpha 3.
yeah, products of
Minus alpha 1, alpha 2, alpha 3.
whatever, minus alpha 1, minus sign will remain here. Alpha 2, alpha 3, minus so on, right? Right. Plus, so on. What about the last one? Last one would be z to the power 0. It would be just you pick alphas from your case. So it will be minus alpha 1, minus alpha 2, so on up to minus alpha n.
Yes, sir.
Now you see you have coefficients now in terms of these zeros. Huh?
Yes, sir.
So what is the coefficient of z to the power n? We have fixed that to be 1. So whenever you want to compare, okay, you have to take out that. Take out the, if you have coefficient here, you have to take it out.
Yes, sir.
So, what do you get? Coefficient of z to the power n minus 1. Okay, let me call it c coefficient of n z to the power c n minus 1. This is coefficient of z to the power n minus 1.
Yes, sir.
What do you get?
Minus times sum of two.
Minus times sum of zeros. Let me call that s. Okay, I'll call it s1 and you will see shortly. Okay, minus s1,
Yes, sir.
which is just the sum of zeros. What is coefficient of n minus 2? Sum of zeros, but take 2's together. Okay? Sum of
Product of two zeros.
yeah. So, but quite simply, I'll just say sum of zeros taking 2's together. Okay? So
S2 is.
S2. So now, do you see why I called it S1?
Yes, sir.
Right now S2. Okay, S2 means take sum of zeros, but in a manner where you take 2, take product, add 2, take product, add. Do all possible of them, right? And then coefficient of what?
N minus 3.
Sum of zeros, but 3 is together, right?
Yes, sir.
All possible 3 combinations, right? Okay, but with a minus sign.
Yes, sir.
Just generalize this. Whatever coefficient of n z power n minus, let's say k, we were writing the n minus 1 and 2. Okay?
Yes, sir.
What about that? What is the coefficient of z power n minus k?
SK.
Sk. But you have taken into account this minus sign, so minus 1 raised to power k.
Yes, sir.
Now if k is 1, you will get minus sign. If k is odd, in the end, what you will get? What is the last coefficient?
Z.
C is C0, right?
Yes,
The coefficient of z to the power 0. It's sum of zeros taking how many together? N minus, right? Because C0 is n minus n, so k is n for that. So sum of zeros taking all of them together, which means just one number, simply one combination. You take all of them, take product, okay? But minus 1 raised power whatever, minus 1 raised power n. Right? Because if they were even on them, then it will be plus.
Yes, sir.
This minus 1 raised power k. K was n for this.
Yes, sir.
समझो? Huh? So do you know how to relate the coefficients with zeros for any polynomial? Huh? Yeah? It's quite simple. Okay? You just take the product and just compare. Okay. Now let's apply this to this equation, this polynomial. Z to the power n minus 1. Okay? Remember we found it 0. It's 0 is where z to the power n equals 1, the nth roots of unity. Okay? What were they? They were omega m, where omega m was e power 2I m pi by n. Right? Does this make sense?
Yes, sir.
What do you know here? You know the coefficients, right?
Yes, sir.
Because you know the polynomial, so you know the coefficients. What is the coefficient of z to the power n? It's 1. Good. What is the coefficient of z to the power n minus 1?
0.
0. Z to the power n minus 2?
0.
Z to the power n minus 3?
0.
All of them are 0. Okay?
Yes, sir.
Good. But you know the zeros also. Okay? Therefore, you can write equations between these zeros and those coefficients. That will give us some equations, some relations for this. Let's first find what is the coefficient of z to the power n minus 0, n minus 1. Coefficient of z to the power n minus 1, it is 0. Right?
Yes, sir.
But what was that? It was the sum of the zeros taking how many together? One of them together, which is just the sum.
Yes, sir.
Minus of that. Okay, it will depend on n. Right?
Minus 1 power.
Minus 1 to the power n
Yes, sir.
times sum. Sum is basically the zeros are omega m's now instead of alpha m's. That sum over m runs from 1 to 0 to n minus 1. Right? Omega m. Okay?
Yes, sir.
Yes, sir.
But this minus 1 to the power n just drops out, right? It's pointless because it's 0 on the other side. What do we get? And when you add nth roots of unity, what do you get? Okay? This is fine?
Yes, sir.
Huh?
Yes, sir.
Okay. Let's try to visualize this equation, okay? You'll see something familiar. What are these complex numbers? What is the first one? It is just 1. Okay?
Yes, sir.
What is the second one? It is just 1 but rotated by how much? Its modulus is 1, good, but its argument is 2 pi by n. Right? And then 4 pi by n. And then
6
till you complete. Okay?
Yes.
Let's just do n equal 3 cube roots of unity. This is nth root of unity. I want to do n equal 3. And this will tell me sum of the 3 roots of unity is what? 0. Right? So let's see how to get it. The first one is just 1. Right? What is second one? 2 pi by n is 3.
2 pi by 3.
Which is where there? 2 pi by 3 is how much? 160. No, sorry, 120. Pi by 3 is 60.
Yes, sir.
And 2 pi by 3 is how much?
No.
Suppose that's right. Huh?
120.
120. It's just representation purpose, so it has to be here. Right? 120. है ना?
Yes, sir.
ये एक है, ये दूसरा है. Okay? What about the third one?
Pi.
No.
3 pi by
0. So m is what? 0, 1, and 2. 4 pi by 3. 4 pi by 3 and 3. What is 4 pi by 3? 4 pi by 3. That is 4 in degrees, it is 4 times 60. That's what?
240.
240. Where is that? Here, right? Because this is 370. Here, this is
270.
270. That has to be here. 120, 240, and back to 360. Okay.
Yes, sir.
But sum is there adding these 3 complex numbers. Correct?
Yes.
But remember, complex numbers add like vectors, right? You x1 plus x2 plus y1 plus y2. X components को add करना है, y components add करना है. ठीक है ना? So instead of thinking them as complex numbers for a while, I can just think of them as vectors, right? So 3 position vectors I have to add. This guy, and this guy. Right? What is their sum? What is their sum? The sum is 0 obviously, right? But remember, when you add vectors, remember polygon law.
Yes, sir.
Right? These are vertices of a polygon. What polygon is that? Triangle. Right? These are vertices of a triangle.
Yes, sir.
You know? when we add all the position vectors of the vertices of a regular polygon, we get 0, 0. Right? Why? Because they cancel each other pair. Okay, इसमें तो दिखाई नहीं दे रहा है, ठीक है ना? But you will see, let's say for example, if you do n equals 6, you will have 1. Then what?
6 by
What are the arguments?
2 by
Because
6.
modulus तो 1 ही रहेगा, हाँ?
2 by 6.
2 pi by 6, which is how much? 30. ठीक है ना? है ना?
Yes, sir. 5 by 6.
30. Good. Then it will be 60. 3 pi by 6, 60. So very bad prime. Then 90. Then 90. Maybe I should draw it better. Then what? 120. 120. Then 150. 150. Then 180. 180 is here. Okay. 210. 210. Then where? 40. And 270. That's up by X, na? 300. 330. 360. Now see, they cancel pairwise. 1 minus 1.
Yes, sir.
Right? This guy will cancel this guy. Right? They cancel pairwise. This cancel.
Yes, sir.
So all the vertices of a regular polygon, when you add them, becomes 0. Right? It's very obvious for even. For odd ones, you just have to show that this component cancels this guy.
Yes, sir.
The sum of these two cancels this guy. Right? Which is indeed true if you just add these two vectors. These two. Right? Or you don't need to add them. You can use maybe I don't know, triangle law or something to add. It's not difficult to show. Okay. Now if I add this and this, what is the resultant? Vectors, 2D vectors, right? If I am adding this and this, what is the resultant? It's this.
Yes, sir.
Right?
It's the opposite.
Yeah, आपको ऐसा polygon बनाना पड़ेगा, right?
Yes, sir.
And then this will like, see, it's already opposite to this.
It will cancel.
It will cancel. Okay?
Yes.
It's a bit, we have worked a bit, or it's a bit more non-trivial in some sense to show. For odd ones, even ones is obvious, right? Because everything is cancelled in pairs.
Yes, sir.
Right? This guy cancels this. So now do you accept that this is indeed true? We derived it algebraically, and then we visualized it what? Graphically. That is indeed true. Right? Good. So what is the sum of nth roots of unity?
0.
0. Cube roots of unity?
0.
Any roots of unity?
0.
0. Okay. Good. Now, let's do the other one. What's the coefficient of c to the power n minus 2? Okay. What is that? Huh? It is 0. Right? But this is in terms of roots, what's it equal to? Sum of zeros, taking how many together? Taking 2's together. So how do I write that? Sum over m comma n. Right? Because, sorry, not n I'm using already. Sum over m comma m prime. Right? Okay? Huh? Because these zeros are labeled by these integers m, which go from what? 0 to n minus 1. Both go from n minus 1. But when I'm taking products, you can't take same, right? Sum of zeros taking 2's together, you can't take same. Remember, these follows, this came from this taking different, right?
Yes.
Taking same means you are making two choices from the same bracket. That's not allowed, right? Remember? You get my point. So sum of zeros taking all of them, so it takes 2 of them together, but none of them should be same, right? Which is obvious because you never got alpha 1 square here. Okay?
Yes, sir.
So here what should be the condition?
Omega
M prime should not be equal to m. Right? The condition, you take the sum or n and m prime, but then you don't take them to be same. And you have to multiply omega m with omega
M prime.
and you get
0.
right? But can I put omega and omega m comma m prime equal to 0 to n minus 1, but do not take them to be same, m not equal to m prime. And what do I get? What do I get? E power 2i m pi
Divided by
n
into e to the power m prime
2i m pi divided by
m prime.
m prime, right?
Yes, sir.
And this should be 0. So that gives me sum over m, comma m prime from 0 to n minus 1, but do not take two of them together. So m not equal to m prime. Okay? E to the power 2I m plus m prime. So this guy is okay? Right? But I want to get rid of this m not equal to m prime. Okay? So how to get rid of this? I add m equal to m prime terms. Okay?
Yes, sir.
So I add the same number of terms, same terms. No, this is fine. Let's just keep it. So this is another identity. If you take products and take twos of them together, then what do you get? You get 0. Okay?
Yes, sir.
So another identity. Right? Taking omega m and omega n, take products. Okay?
Yeah.
Take twos of them together and then okay?
Yes, sir.
Now okay, maybe we can do that later. Let's just continue this part. So now what should I do? Taking three of them together. What is quotient of z to the power n minus 3? 0. So if you take omega n, omega m, so if you do sum over m prime, m double prime, but there is a thing that you have to remember that none of them can be together. It will be same. So omega m prime, omega m double prime, this is also 0. And if it goes on. Okay?
Yes, sir.
Any equation of this form will have the same relation for zeros. But we were doing nth roots of unity. Right? Any equation of this form, right? We have zeros which satisfy these conditions. Right? Take twos of them together, take threes of them together, multiply, add, you will get 0. Okay? Except when you take all of them together. Because then that is this quotient, last one, which is just 1. Minus 1, sorry. Minus 1. So, but this quotient of C0, this quotient of z to the power 0, right? Huh?
Yes, sir.
Now what is that? And that is just product of the zeros. Right? So, what do I get? Omega 1, omega 2, so on, omega m. No, sorry, omega 0, we are labeling from 0. After what? Omega n minus 1. Right? But there is a minus 1 to the power n factor, right? Remember this? Right? This is equal to what? So this if I go there, you get omega to the power what? You get minus 1 to the power n minus 1 of the if I go to this minus 1 to the power n, just keep it as this. If I take it there, you will get minus 1 to the power 1 minus n or something. The same as minus 1 to the power n minus 1. So this is what product of zeros gives you. Okay? Let's say n is 3. Okay? Then this will become, so how many zeros will I have? 3. Omega 0, omega 1, omega 2. These are cube roots of unity. Okay? And this is what? Minus 1 to the power?
Minus 1.
This is just minus 1. And what is this?
1.
Well, this is product of 1. It just cancels the minus signs on both sides. Okay?
Yes, sir.
So product of cube roots of unity is just 1. Okay? So what are these cube roots of unity? Let's try to figure them out because we know, right? So what is the first one? So what are the general solutions? What is omega m? E to the power 2 pi I m by n. N is 3 because we're doing cube roots. Okay?
Yes, sir.
Huh? Okay. So what is m? So what is the first one? What is omega 0? 1. Enough?
Yes, sir.
1 ka cube root is obviously 1. Okay. What else? E power 2 pi I by 3. E power 4 pi I by 3. Right? Is this this already?
Yes, sir.
Huh? Does this make sense?
Yes, sir.
Huh? This is fine, right?
Yes, sir.
So sometimes people represent, so this is omega 0 and this is omega 1 and this is omega 2. Note that omega 2 is just square of omega 1. Right? So sometimes people denote cube roots of unity as 1 omega omega square. Because you really don't need two symbols. You only need one because this one is just square of this. Right? If I square this, does this ring a bell? Have you ever heard 1 omega omega square are cube roots of unity? Huh? Right?
Yes, sir.
Good. I spent too much time doing nth roots of unity, but anyways, maybe it was worth it. Okay? Huh? Good. So this is basically all the basic things I did with complex numbers. Okay? I still have half an hour left. Because in half an hour, okay, fine. So maybe I need to do some simple things. I'll just quickly introduce complex functions. Okay? Now, see, I already wrote some complex functions, you just didn't even notice, it. Okay? For example, I wrote a polynomial, which is a complex function. Right? It takes input as a complex number and gives you output as a complex number. Okay?
Yes, sir.
Is it okay?
Yes.
So, for example, let me consider a simple complex function f of z equal to z. Okay? Okay, so we should be careful that there is a formal definition of functions which mathematicians give. Okay? So I am using very vague terminology by saying its input is a complex number, output is a complex number. Okay? But there is a precise meaning to this word function. Okay? What was it for real numbers? Do you remember? Right? That there is it's a special type of relation between one set to another. Right? But there are some conditions this relation should satisfy. Right? Huh? Not one. Then every there should be an image for every pre-image. Right? It means the number, the input, there should be no input which does not give you output.
Yes, sir.
Right? Huh? Right? There could be outputs with no inputs. Right? That is okay.
But no input without.
There should be always input should have an output. Only then you can call it a function. Okay? When you have an input as well as an output, so for every input you have an output, and for every output you can find an input. Right? That's called what? Onto function. Okay? That's called onto function. Huh? Now for every input, if you have a single output, and for every output you have a single input, that is one, as well as onto. Okay? Is this clear or shall I repeat?
Yes.
Huh? No, there is no meaning on it, right? No. See, if you have, so first you have to relate two sets of numbers, right? So let's say this is one set, this is another. Okay? Huh? So let's say I have 1, 2, 3, 5, 6, 7. Okay? So these are my inputs, and this is output 6, 7, 8, 9, whatever. Something like that. Okay? Okay, I am taking finite meaning. Now, a function, a relation is basically you are associating these, you are creating ordered pairs and creating a new set where there is a relation between these two. Right? X and Y. X belongs to this and Y belongs to this. Okay? Now, a special kind of relation is called a function. Okay? And that relation should have these properties. Okay? For every input, there should be an output. There should be an output. Okay?
Yes.
And no input should give you two
Without
outputs. Something I forgot earlier. Okay. So, this is allowed. This is okay. Yes.
Three.
Yeah, but this is okay. Two inputs can give you same output. Okay? Huh? But no input should give you, so there shouldn't be something like this. Like this is not allowed.
Yes.
One cannot give you 2 outputs. Then you can't call it a function. It may still be a relation, yeah, sure, but
not a
it won't be a function. Okay? Then there are types of these functions. Okay, one type of function is where this is also not allowed. Right? Then no 2 inputs give you the same output. That is called 1-1.
Yes, sir. Yes.
That is called 1-1. Now, and then there is another function, another type of function, where this is not allowed. 6 does not have an input. That's called onto.
Yes, sir.
And the function which is both 1-1 and onto, okay? Think of that function. Every input has a single output. Right?
Yes, sir.
No, sorry, every input has a single output. In some sense, there are no 2 inputs which give the same output. Okay? And every output you will be able to find an input.
Yes, sir.
If you think of it, then such functions are basically called invertible functions. Okay?
Yes, sir.
Basically, f is a function, so is f inverse. Right? For example, if you have this, right?
Yes, sir.
F is indeed a function. Every input has an output. Okay? Every input has an output, and no 2. Okay, not every 3. I forgot. It was lazy. Okay. Every input has an output, right? And there is no input which has 2 outputs. Okay? Good?
Yes, sir.
But if I think reverse, if I want to think of it as a function from here to here, right? First it goes away because 6 is not there. 6 does not have an output. So the function already goes. But let's say if I fix that problem, if I remove 6, okay? There's still a problem. Right?
Okay,
7 has 2 outputs. Right? So these both things should not be there. Right?
Yes, sir.
Right? So every input should go to an output. Yeah, and no 2 inputs should have same output, as well as that every output should have some input. Okay, this input-output line may be a bit confusing, but think about it. Okay. Now this was a simple example where the set I wrote was countable. Like I put some numbers by hand and I associated them with some rule, some random rule. Okay. But typically functions that like physics people are concerned about are basically functions on a real line.
Yes, sir.
Okay. Okay. Or functions on a complex plane. Okay. Functions on real line means your domain and codomain are basically real numbers. So inputs are outputs are coming from sets which are real sets, basically real numbers. Okay.
Yes.
There you can't randomly associate numbers like I did here. You need to have a rule. Right? You can't randomly associate numbers from a real line to real line. That's too much information. Right? I can't give you all possible ordered pairs. Right? You need to have a rule. And the rules you know, those are your simple functions. For example, f of x equal to x square. So the rule is take your number from the real number set and square it. That is your rule. Okay? The same ideology gets transferred where? To complex functions. But your inputs come in from a complex plane, no?
And outputs are also complex.
Outputs are also complex plane. So there are 2 complex planes. Just like you had 2 real lines, which one contained inputs and contained outputs. So 2 complex planes. Right? Okay? This will have inputs. Okay? Basically your Z. Okay? And this will be your outputs. Okay? Okay? A number here, okay?
Yes, sir.
Might be mapped to some number here. Okay? Mapped in the sense that this number, this input has that output.
Yes, sir.
Right? Some other input has that output. Okay? We'll try to visualize some functions later. For now, we just see that, okay? But we need to have some rule of associating. Okay?
Yes, sir.
Those rules are basically, we can take similarly, we can take rules similar to, real functions. Okay. For example, let's consider simple one. F of z equal to z square. Let's square the complex number.
Yes, sir.
Okay. Just take the complex number and square it. Okay? Remember, f of z is nothing, it's also a complex number, right? Now it's written in a fancy manner. Why? Because f is a complex number which depends on what z is, right? That's why it's, but eventually it's a complex number. So it will have a real part as well as an imaginary part. Okay? And those will be functions of real part and imaginary parts of what? Z square. Okay, z square. Okay? So let's try to see. So if z is, let's say, x plus iota y, what is f of z? Can somebody tell me? It is x plus iota y whole square. That is a square minus b square. Well, add a square is minus 1, right?
Plus twice iota x1.
What is it? Right? Okay? So what is the real part of f of z? It's x square minus y square. What is the imaginary part?
Twice x.
Twice x square. Okay? Remember, these are real numbers. That's why you are able to say this is the imaginary part. Without the iota, and this is the real part. Okay, sir. X and y are real. Huh?
Yes.
Think now. Let's try to visualize what number goes to what number for f of z equals z square. Okay?
Yes.
Is it fine?
Yes, sir.
So this is my z. This is my f of z, which is just z square. Okay?
Yes, sir.
Tell me some number. Some number. Let's talk about this one. If z is 1, where does 1 go? 1 goes to 1. Right?
Yes, sir.
What about any number? Let's say here. Let's say this guy. Let's say it has some modulus r and it has some argument theta. The reason I shifted to polar will become obvious now, because this looks a bit complicated for now. Okay? So what is this? So f of z is what? So z is basically, for this one, z is what? R e power I. What about z square? What about z square? Can you square this? E power 2 I theta. So what is the length of this new vector? R square. Sorry, not length of the vector, sorry. What is the modulus of this new complex number? It is r square. So it is r square. Okay? And argument? 2 theta. Exactly. So if this was theta, it's double that. Right? So double that. Huh? So this point goes to this point. 2 theta. Right? So this is mapping points. Right? Huh? I can map curves as well. Okay?
Yes, sir.
I can map curves as well. Curves in the sense, let's say if I take those points on the z, okay, which form a circle. Right? I could take points which are on a circle, right?
Yes, sir.
What are those points? Those points are mod z equal to 1. Let's say if the circle has radius 1, right? So basically the equation is x square plus y square equal to 1, but x square plus y square is just mod z square. So mod z square, that gives you mod z equal to 1. Okay? What about this guy? What will happen in the other plane? What will happen in the other plane? Look at every point. This should become r square, but r is 1, so it will remain as it is. What about theta? Double हो जाए. So all the circle will have double shape, right? It will just rotate like this, right? Nothing else. The circle, so the circle will also become the circle will become a circle. All the points on the circle will get mapped to the points on the same circle. Okay. So you can also see that if mod z is 1, right? Mod of f of z is also mod of z z square, which is mod of z ka square, right? Which is mod z is 1, mod of f of z is also 1. So all the points f of z are also 1, right? You can map curves, right? Let's take this line, the real line. Okay? What is real line? X equal to constant. Real part of z equal to constant. Sorry, real part of z equal to, sorry, imaginary part of z equal to 0.
Imaginary 0 and real.
Imaginary part of z equal to 0 is this line.
Yes, sir.
Right? This is the equation for this line. Huh? What about z square? Where would this line go? Okay? Huh? So imaginary part of z is 0. Okay?
Yes,
It means let's go there. Y is 0.
Line A.
Huh? What do you get? If y is 0, what do you get? What is f of z?
X.
X square. What is that?
This line straight.
F of z. F of z is basically x square.
X square.
If z lies on one real line,
Real line.
अगर तो यहाँ पर point real line है, then f of
Real line. X square.
x square. What is that?
Line. F of x is a parabola.
X square. Still, no, it's not a parabola. It's still a line. And these points form a line.
Length square.
Right?
Yes, sir.
So this line gets mapped to
This line.
right? But the points are mapped here and there. So 0 will be mapped to 0, 1 will be mapped to 1, and so on. Right? 4. Right? That you have to see. Okay?
Yes, sir.
But this is not trivial. I want to know what happens to something. I want to know what happens to something a bit more non-trivial. Okay. Yeah. Okay. What about this line? X equal to y means x equal to y means real part of z equal to imaginary part of z. See, x equal to y is a line, right? I can rewrite this line by equation in terms of the z, in terms of z, the complex number. Basically, you put x as z plus z bar by 2, x is the real part, and y as z minus z bar by 2. Okay? So this is basically a line equation. This is x equal to y, or in other words, real part of z equal to imaginary part of z. Okay? Well, how else can I write it? I know x is z plus z bar by 2, y is z minus z bar by 2 iota. Right? This is also the equation on the same line. Okay? But let's take x equal to y here. What do I get? If x equal to y, this is 0.
Yes, sir.
What is this? 2 iota?
2 x square.
2 iota x square. Right? What is that? Imaginary line.
Y axis.
So this axis is mapped here. Somebody know?
Yes, sir.
It's mapped here. This guy goes here. Okay. So you see, I mean, you will learn later on that these mappings that we are doing are very interesting and they could be used to solve some problems in physics. Okay? These are very elementary mapping. Okay?
Yes, sir.
Okay. We'll do more mappings when we learn more functions. Okay? Okay, good? So one rule, what do you see? This, right? This is one rule, f of z equal to z square, right? So notice that if I want to keep a pin on this mappings now, because we'll do more mappings when we learn more functions, okay? But can you see that this function f of z, right? Okay, is basically a combination of two scalar fields. If you remember, scalar fields, you have a two-dimensional coordinate system. With every point you associate a number. Now see, with every point you are associating two numbers, the real part and the here. With every point you are associating, right? It's a combination of two scalar fields, right? One, right, is the real part of this complex function. The other scalar field is the imaginary part of the complex function. Okay. So all the things that you learned in 2D scalar fields will work here as well. But you have to be careful that there are two of them. You have to do one separately, another separately. Okay. So in general, function f of any function, complex function f of z, I can write it as u of x comma y is a scalar field. Okay, a real scalar field. Real, u has to be real. Okay, plus what? Iota times some v of x comma y. What is this? X and y. This is dependent on x and y. And this x and y is dependent on x and y. Okay.
Yes, sir.
Whenever we learned, see, you did 1D functions, right? What did you do immediately afterwards? Derivatives.
Yes, sir.
When you do 2D, when we did scalar fields, right? What did we learn about? Derivatives, how to take its derivative, right? Then you learned that, okay, I need to take a directional derivative, right? The derivative depends on which direction I am looking at. Okay?
Yes, sir.
Well, now we are in a complex function. What is the most logical next step? I should think about derivative. Okay? So let's consider some complex function. Huh? And how do you take derivatives? You basically first compute how much the function changes when you change the argument. Okay?
Yes, sir.
So let's say my z is x plus iota y, and I move from z to z plus delta z. Okay? Z plus delta z, which is x plus delta x, iota plus y plus delta y. Okay? Okay?
Yes, sir.
Is this fine? Delta z is delta x plus delta plus delta. Whatever, delta x plus iota y plus so z is basically x plus iota y. Delta z is another complex number, which is small change in the z. Okay, and it's represented as delta x plus iota delta x. Okay. So how much will the function change? It will be f of z plus delta z minus f of z. This is just simply change.
Yes, sir.
But this guy, maybe it's difficult to handle. I'll just go back because I know scalar fields, real scalar fields, right? So this is basically u of x plus delta x. Right?
Plus some degree.
Plus y plus comma y plus delta y minus u of x comma y from this, right?
Yes, sir.
Plus iota, what are the imaginary guys? V of x plus delta x, comma y plus minus v of x comma y. Indeed, right?
Yes.
Now, what about this guy? This change. Remember how do you calculate the change in the change in what? Change in this? Change from going from, if you remember, scalar fields.
Delta x.
Yeah? Delta
Delta
x.
x understood.
Yeah, the derivative,
Understood.
the directional derivative, right?
X times.
Huh? You have to multiply with the length.
No.
Yeah? Yeah. So what does that finally give? So dx of u times delta x, right? Plus this was it. From here we define the directional derivative. Right? You take mod of the change, mod of delta square root, delta s square, delta y square, whatever is left is directional derivative. Plus what does the other way? D partial x of u is partial derivative of u. Okay?
Yes.
And I just didn't write the arguments. It becomes too long.
Yes.
And what do I get? Partial x of v delta x plus partial y of v delta y. Alright? Is this fine? Can I see? I have delta z is what? Delta z. What is delta z? What is the change in the complex number? Delta x and delta y are changed in the real parts and imaginary parts, right? Because but I am doing everything in what? Complex numbers, right? Huh?
Yes.
So I should try to write everything in terms of complex numbers, right? So delta z is delta x plus
Delta y.
and delta y. This is a change in the complex number, right?
Yes.
Huh? So I want to exchange delta x for delta z, right? But you may ask that why don't you exchange delta y for delta z, right? Okay? We will do both. Right? We'll see what we get. Okay?
Yes, sir.
Is that fine? So can you change instead of delta x? Can you put delta z? What do you get? Partial x of u delta z minus I delta y, right? Okay? Plus
Delta y.
dy delta dy of u delta y
Minus delta x.
plus iota delta z together, delta z terms. What are the delta z terms? I get partial x of u and what else? Plus add the partial x of v. Okay? This is the delta z term. Right? Yes, sir. Plus, what do I get for delta y? What do I get for delta y? Can you tell me the term? What do I get for delta y? What are the things? But the जिनके साथ delta y आता है, you must say that delta y.
Minus iota times
Minus iota times
delta x.
u partial x of u. Okay. What else? Plus
Partial
partial y of u. Right? And what else? Plus, yeah, with this
delta v.
iota square and
Delta
delta
x
x
of u.
delta x of v
Yes, sir.
plus
Delta y of v.
del y of no iota x. Okay, good. Right? Huh? You people do this. You people substitute at home. I substitute delta x in terms of delta z. But delta y was not because there are two variables, delta x and delta y, right? You do the other way. Delta y की जगह you put delta z minus and delta x. ठीक है ना? You will see that the conclusions would be same, whatever conclusions I'm going to make. Okay. Now what is that? The directional derivative of what? Of scalar fields depend on what? The derivative of scalar fields makes sense only when we talk about direction, right? Which direction, right? So grad n hat dot grad is your derivative, basically the directional derivative, right? Of any scale. So in general, complex functions, it's a combination of two scalar fields, real scalar fields. One forms its real part, another forms its imaginary part. So in general, इसका भी directional derivative किस पे depend करेगा? Which direction are you talking about? Right? ये complex numbers, this f of z, this complex number, the way it change, would in general depend on what direction it is. Right? Yes. But see, that there is one case where that does not, that is no longer true. You don't need to talk about direction. That case is when this guy is in. This whole thing. Okay? Let's say for a second, this u and v are such that this guy is 0. It could be 0, right? It may not be 0, right? Right?
Yes, sir.
But for now, I assume that this whole thing is 0. See what do I get? I get f of z plus delta z minus f of z is what? Del x u plus I del x v times what? Z. Right? Look, think about the real functions. F of x plus delta x minus f of x was something which was the derivative. Right? Yeah, f prime, whatever, derivative times what? Is there any difference? Huh? Right? There's no difference. Right? So I can actually define a derivative here. Same in exactly the same manner. Complex real scalar fields के लिए there was slight difference. Right? You need to define a direction and then take the derivative. Right? N dot grad. Right? Many good things came out of that as well. Right? But here you see, this is exactly the same manner. I divide by delta z and then take what do I do to make it a derivative? Delta z to be 0. Right? Yes, sir. So I can, just like I did for this. You study the change and then divide by the change. That gives you the rate of change. Right? And then take that to delta x to be 0. Right?
Yes, sir.
So I can do exactly the same here. Right? I can take limit delta z tends to 0. F of z plus delta z minus f of z divided by delta z equal to this guy. This something partial x of u plus partial x of v in terms of u and v. So this guy is what? Derivative. No, this is no longer derivative. There's no direction here. Right? It's just derivative. This is d of y. But for now, just look at the interesting consequence of assuming that is 0. Then I can treat my complex function as if it was a mechanically, as if it was a real function. And I was able to define df by dz. Right? Huh? And one way to calculate df by dz is take this partial x of u, keep v fixed. Why you keep fixed y? Partial x of u plus iota partial x of v. Right? Huh?
Yes, sir.
Okay? Is that fine? Now, let's go back to this. So I defined a derivative. Okay? Huh?
Yes, sir.
Remember, you will see later on that this d by dz, I can take d by dz as if I am differentiating a real function. Okay? For example, f of x equal to x square. What is df by dx?
2x.
2x. Right? If you have a complex function f of z equal to z square, what is df by dz?
2x.
It's 2xz. Right? Just a natural extension. I'll teach you how it was 2xz. Right? But there is another way of computing this. What? This thing. So let me quickly do this, and then I will count why that. See what does that do? Then we will discuss this term. So I take f of z equal to z square, and mechanically this derivative is the same as, right, as if you are differentiating real numbers, right? So what is df by dz? What do you expect it to be? 2z. This is computed at a complex number now, right? At some complex number z.
Yes.
But this is also equal to what? Partial x of u
iota times partial x by v.
plus iota times partial x of v. Right? U and v for f of z equal to z square I had calculated. What was that? X square minus y square. Remember?
Yes.
And 2 iota xy, right? Let me not go backwards. It's confusing. So u was what? This is x square minus y square plus 2 iota xy. Right? What is partial x of u?
Partial x of
U. U is this thing, right?
2x.
2x. What is iota times? What is partial x of v? V is this iota over x. 2y. 2y. Yeah, and then 2 will come out. What was x plus iota y?
Yes, sir.
This is the same. Because you are computing this object, which is like mechanically is the same as if you are doing real numbers. Okay? Huh? Okay. Now let's go back to what this other guy gives us. I assume that these are not all possible complex functions. So यहाँ से जो भी theory होगी, this is not true for all complex functions. This is only for some complex functions. जिनमें क्या होगा? They u and v are somehow related to each other, right? What is that here?
Equal to 0.
If this guy should be equal to 0, right? Let's study this. What does that do? Okay. So what was that? Can you tell me?
Minus iota.
Minus iota partial x u
plus partial u
plus partial
y
y u
plus partial x v
plus partial x v
plus iota partial y
plus iota partial y
v
equal to 0. What is this? A complex equation. A complex equation. Every complex equation is equal to what? To real ones, right? So मुझे imaginary part एक side I have to calculate the imaginary part and the real part and then equate them separately to 0. Okay? What is the real part?
partial yu
plus partial x v plus iota times
partial x v
u minus plus partial y.
partial v.
So if this complex number is 0, it means its real part should be 0
Complex part should be 0.
and the imaginary part should be 0. Yeah. Well, complex part, but typically is not real part, imaginary part. So what do I get? Partial y of u is equal to minus partial x of v, and there is something else I get. I get
Partial x u
partial x of u
is equal to partial x v
y v.
partial y v.
Right? So u and v, if u and v satisfy the, okay, this is a more complicated looking equation, right? But these are very simple. The y derivative of u should be equal to what?
Derivative
x derivative of v. Okay, and then x derivative of u should be y derivative of u. Do you get my point?
Yes, sir.
But the real part of the functions is the real part of the functions real part of z say derivative partial x of u is the same as partial y of
Yes, sir.
imaginary part, right? Well, after the cross there, then there is a negative sign.
Yes.
Partial y of u is equal to minus x. Okay. What is the consequence if these two are true? What is the consequence?
Derivative.
Derivative, we can still take, we can always take a derivative, right, for this complex function, but there is another special thing happening. What? The derivative becomes what?
Real.
No, I never said that the derivative becomes. Derivative becomes what? Independent of direction. You don't need to talk about direction. Otherwise, you have to specify what delta y is.
Yes.
Right? Otherwise, there is delta z and delta y also. Right? So you are forced to define a direction derivative.
Yes.
Right? So the derivative becomes what? Independent of?
Direction.
Independent of which direction of change. That effectively makes the derivatives of complex numbers to be analogs to derivatives of real numbers. समझो? This class of complex functions, ठीक है ना? These are not all complex functions. These are a class of complex functions. Yeah? And this is what you have to learn in your entire course, in your entire chapter. Okay? And this class of complex functions are called analytic functions. Analytic functions. They are called analytic functions. Okay? So what are analytic functions? They are derivatives. These are those complex functions whose derivatives are basically independent of direction. You can treat them as, I mean, you can like mechanically do the derivative as if you are dealing with real numbers. Okay? Real functions. Okay? And these equations, okay, when these equations are true, the function is analytic. Okay? There is one more point I would make. But if these equations are true, then the function is analytic. And this is called Cauchy-Riemann equation. What are these called? Cauchy CR equations. In shorthand they are called CR equations. So when Cauchy-Riemann equations are true, then the function is analytic. But remember, these numbers are calculated at a particular point, right?
Yes.
You do partial y of u at some y, and then partial x of v, right?
Yes.
So when you talk about analytic function, you need to talk about which point you are talking about, right?
Yes.
Right? So when you talk about analytic functions, you need to talk about which point you are talking about, okay? So let's qualify a bit my earlier statement, let me qualify that a bit. That point where Cauchy-Riemann equations are true, okay?
Yes, sir.
The function is said to be analytic at that point. Okay?
Yes, sir.
Somebody man?
Yes, sir.
Right? Because it could happen, there could be certain points or there could be a lot of those points जहाँ ये true नहीं होता, or it could be not true altogether. On any point, this may be untrue always, right?
Yes, sir.
Then the function is said to be non-analytic everywhere. Okay?
Yes, sir.
But let's say if you have a complex plane Z, now let's say there are few of these points जहाँ ये true नहीं, right? Then the function is analytic on the entire complex plane except these 3 points. ठीक है ना? So when I say analytic function, I mean I have a domain in mind. I have a
Domain.
मतलब जहाँ ये equations true होंगी,
Point.
ठीक है ना? If I say analytic at a particular point, it means वहाँ पर analytic है, ठीक है ना? Right?
Yes, sir.
Okay. Do you get my point?
Yes, sir.
Okay. So in next class we'll continue with these analytic functions, okay? And we'll see what amazing properties they have. Okay, they are very amazing properties. ठीक है ना? And physics quite often you will use analytic functions. I mean, they are of natural use. The the functions in physics that we will deal with will mostly be analytic. Okay? Analytic. But there would be some non-analyticities. I mean, there would be points here, Cauchy-Riemann equations won't be true. Huh? We'll see consequences of that as well. What happens. Okay? But then next class. Today, this much is enough. Okay? Good. Welcome.